Welcome everyone to this session about data processing. So we are gonna be talking about where Apache Beam is coming from. So where all these data processing systems are coming from, how they evolve, and how Apache Beam is new and different. Here we see all the papers coming from Google Research about data processing, from the first ones about the Google file system, MapReduce, and other data technologies, ending up in Apache Beam that was born in 2015. All these technologies that were published as papers were also implemented as open source, not by Google, but by others, like Hadoop, for instance, was done by Yahoo. All these papers, as I was saying, were implemented as open source processing systems, and these systems became very popular. The fundamentals that are behind these systems and behind these papers are actually still valid for how Apache Beam works on top of the different runners. So let's start talking about MapReduce and Hadoop. MapReduce was an innovation that was born 20 years ago, and that introduced simplification of data processing by assuming that users had to write only two functions, a map and a reduce, and then the system would take care of all the parallelization and all of the shuffling of the data as it was required, depending on the kind of calculations that were made. So as we see here in this slide, let me see if I can put here the pointer. So these are the inputs. The system, through the so-called Hadoop file systems, would take care of splitting the data in different chunks that were small enough to be processed by each one of these functions. This was done automatically. You didn't have to do this. And this was already an innovation. So the map function was executed for each one of these elements. The output was another element that it was transformed with a key. So here we have these key values. And then the system shuffled the data to make sure that each one of the reducers got all the elements with the same key. Again, users didn't have to worry about the shuffling. This was done automatically by Hadoop. And then the reduction was done and the final calculation was ready. With this, there were lots of complex calculations that could be done very quickly in a cluster with affordable computers like regular PCs. So this was really an innovation compared to the large-scale data processing technologies that were available before Hadoop and before MapReduce. However, this was still a little bit limiting because here you could just express one function for map and one for reduce. If you needed to do something more complex, you couldn't just with one job. So you had to do complex jobs, complex pipelines with chaining several jobs together. By doing this by hand in your own code, the system wasn't able to optimize how the data was processed across stages. And this was, let's say, inefficient. This may look like a small problem because, well, so here we have like 4 or 5 boxes connected together. But very soon, in complex use cases, users started to write pipelines, combinations of jobs that they had hundreds of stages. And this was a problem because the data processing systems could not optimize different stages together. So each one of the stages was an independent piece that it couldn't be changed in combination with the others. It couldn't be automatically optimized. Despite these limitations, Hadoop was super popular. There were different versions of Hadoop. If anything, the only problem that Hadoop had is that it was complex to write these complex pipelines because you had to write lots of different jobs. The code had to be written in Java. It was very verbose. For doing relatively simple tasks, you had to write a lot of code. So there were lots of innovations that appeared to try to reduce the complexity of Hadoop. For instance, let's mention here a few. Here I'm linking to one of the talks about why Hadoop needs Scala. This is a talk that mentions a couple of frameworks to simplify the development of Hadoop pipelines. And one of the innovations was switching the language from Java to Scala in order to make the code less verbose. Some companies like Twitter created Scalding also with the same goal to simplify the development of pipelines. And Hadoop also, because the jobs were in a way disconnected between them. Every time you had to connect a job with another one, you had to write the output to one step, and then the next step would take the materialization of that data and would read it. So basically, every time you had to move data from one step to another, you had to materialize it in disk, in the Hadoop file system, HDFS, or wherever you were processing data. Materializing data in disk is slow, really a slow operation. As an innovation, Spark attempted to reduce the number of times data was materialized, attempted to minimize data materialization in order to speed up things. And it had much better performance than Hadoop in complex pipelines because it avoided materializing data when it could. At Google, there were another system that was very similar to all these systems. So at Google, inside Google, there were the same problem. And Fluent Java, for instance, is it's a framework that is very similar to one of the frameworks that we have seen in the previous slide. And it's one of the papers that was mentioned in one of the first slides. The main concept behind Fluent Java was the creation of higher level pipelines that combine together steps. Like, for instance, here we're reading from a database or from the file system, doing some filtering, doing some joins, comparing, and then writing one or more outputs, whatever. So you could express any complex pipeline as a single object. But at the end of the day, these were all MapReduce jobs. Another innovation of Fluent Java, it was that before trying to run these MapReduce jobs, it could also analyze the workflow of data, the data flow of data throughout the pipeline, and decide to do changes in the physical execution of this pipeline to try to optimize performance. For instance, typically a naive mapping of this pipeline to MapReduce would be what is shown here in the slide. Each step is a MapReduce job, but it could be also, for instance, optimized like this. And this minimized also the number of times data was materialized. For instance, so here there are 6 shuffles, 6 reads and 6 writes, so 6 materializations of data and 6 shufflings. Here, where there's only one shuffling, not materialization, and 2 materializations of data. So this pipeline executes much more quickly than this one. So that's an improvement in performance. This is one of the bases of Apache Beam for batch execution. There's another one that's also called Millwheel. Millwheel was a similar system to the previous ones to execute complex pipelines, but focus on streaming low latency processing and accurate data processing. Back in the days when these systems were created, it was accepted that stream processing was going to be always inaccurate. If you remember, for instance, you may have heard of the Lambda architecture, where there were a batch pipeline and a streaming pipeline. The batch pipeline was slow but accurate, and the streaming pipeline was fast but inaccurate. And then at the end of the pipelines or of the architecture, you had to reconcile both pipelines when data was ready from the batch in order to amend the inaccurate output of the streaming pipeline. These days, this doesn't make sense anymore because Apache Beam unifies the batching and the batch and the streaming processing systems. You will see this in other talks in the Beam College these days, or you may have probably already heard. A very quick introduction about Apache Beam before finishing. So Apache Beam is a multi-language, multi-runner system that unifies stream and batch processing. You may write your pipeline in Java, in Python, Go, SQL, Scala, and other languages. You may even combine different languages in the same pipeline with cross-language transforms. You may use machine learning workloads, and there are lots of transforms now for machine learning, for instance, and then you can run it anywhere that is supported by Apache Beam, including Dataflow, Flink, Spark, and all the main data processing systems. So this was the history of where Apache Beam is coming from. I hope this was interesting for you. Now it's time for you to focus on the future, on what Apache Beam is able to do, not where it's coming from. Thanks all for your attention.